Welcome to G Fun Facts Online. Today, we're journeying deep inside our celestial neighbor, Mars, to uncover a story of cosmic violence written into the very bones of the planet. For years, NASA's InSight lander listened to the faint tremors of Marsquakes, and what it heard has rewritten our understanding of the red planet. It revealed that beneath the silent, rust-red dust, Mars has a chaotic, lumpy, and tumultuous interior, a stark contrast to Earth's well-mixed mantle. This lumpy heart is a time capsule, preserving the scars of a violent youth and offering incredible new clues about the chaotic history of our entire solar system. On Earth, the constant churning of plate tectonics recycles our planet's crust and stirs its mantle, effectively erasing the evidence of its earliest days. But Mars is different. It's smaller, it cooled more quickly, and its crust solidified into a single, stagnant lid, sealing away the secrets of its formation. This geological stillness means Mars holds a frozen record of its violent beginnings, a record that InSight has finally allowed us to read. The data showed that seismic waves from Marsquakes were systematically delayed as they passed through the deeper mantle. This pointed to the presence of subtle, kilometer-scale variations in composition. In simple terms, the Martian mantle is filled with lumps. These lumps are thought to be ancient fragments, some up to 4 kilometers wide, remnants of a time when Mars was pummeled by cataclysmic impacts. These events were so powerful, they literally fractured the planet's interior, mixing chunks of the crust and even material from the asteroids themselves directly into the mantle. The distribution of this debris is what scientists call fractal, like shattering a piece of glass, a few large shards and countless smaller fragments, all testament to the overwhelming energy of these ancient collisions. One of the most striking features of Mars, visible even from Earth, is its great hemispheric dichotomy. The planet is fundamentally split in two. The southern hemisphere is a heavily cratered high-altitude landscape of ancient crust. In contrast, the northern hemisphere is dominated by smooth, low-lying volcanic plains. For decades, scientists have debated why. Two main theories emerged: a single, colossal impact, or a long-term process originating deep within the mantle. The giant impact theory is easy to visualize. It suggests a massive object, maybe the size of a dwarf planet, slammed into the northern hemisphere of Mars early in its history. This impact would have blasted away the original crust, carving out the vast basin we see today, which later filled with lava flows. This would explain the roughly elliptical shape of the northern lowlands. However, the new data from InSight seismometer has given significant weight to the second theory, an internal or endogenic origin. By analyzing how seismic waves weaken or attenuate as they travel, scientists discovered a major temperature difference in the mantle beneath the two hemispheres. The mantle under the southern highlands is estimated to be around 1,000 degrees Celsius, while under the northern lowlands, it's a much cooler 800 degrees. This hotter mantle in the south would be less viscous and more dynamic. This finding strongly supports a model called Degree 1 mantle convection. Imagine a single, massive plume of hot mantle material rising and pushing up the crust in one hemisphere, while cooler material sinks in the other. This powerful one-plume engine could have been strong enough to create the dramatic, planet-wide difference in elevation we see. Of course, it's also possible the two theories are linked. A giant impact could have been the trigger that initiated this unique pattern of mantle convection, creating a hybrid origin for Mars' greatest scar. Another profound scar on Mars is the Hellas Planitia, a colossal impact basin in the southern hemisphere. At over 200 kilometers in diameter and more than 7 kilometers deep, Hellas is one of the largest and best preserved impact craters in the solar system. Its formation around 4.1 billion years ago was an event of unimaginable violence. It was carved out by a collision with an asteroid likely over 100 kilometers across. The impact would have vaporized and excavated a massive amount of crustal material and sent shockwaves deep into the planet, further contributing to the chaotic, lumpy state of the mantle we now detect. Hellas, along with the thousands of other craters that pockmark the southern highlands, are relics of a particularly violent era known as the Late Heavy Bombardment. This period, from about 4.1 to 3.8 billion years ago, saw a dramatic spike in the rate of asteroid and comet impacts on all the inner planets. The first evidence for this lunar cataclysm came from the dating of moon rocks brought back by the Apollo missions, which showed a clustering of impact melt ages right in this time frame. While Earth's geology has erased most of its oldest craters, Mars's ancient, preserved crust serves as a crucial witness plate for this violent epoch. Its battered surface is a museum of the early solar system, and its chaotic mantle is the direct, internal consequence of this intense pummeling. Each impact was a blow that helped shatter and jumble the planet's insides, creating the heterogeneous mixture we see today. But these impacts weren't just destructive. They may have also been delivery systems, bringing significant quantities of water and organic molecules, the essential ingredients for life, to the young planet. Now let's travel to another ancient landscape, Arabia Terra. This vast upland region in the northern hemisphere is one of the oldest and most heavily cratered terrains on Mars. Its complex surface of eroded craters and canyons points to a long and varied geological history. Here, scientists have found extensive layered rock formations, suggesting a past that involved volcanic ash, wind-blown dust, and perhaps even sediments settling at the bottom of ancient lakes. Most intriguingly, Arabia Terra contains features that resemble terrestrial supervolcanoes. These aren't the cone-shaped mountains we typically picture. Instead, they are massive low-relief depressions called calderas, which are the hallmarks of colossal explosive eruptions. The fine-grained ash and outgassed sulfur from these ancient eruptions could have formed the altered, layered, sedimentary rocks we now find all over the region. This points to a period of intense volcanic activity in Mars' early history, all fueled by the heat and turmoil within its chaotic mantle. The presence of hydrated minerals in these deposits also points to the significant role of water in this ancient landscape, perhaps as groundwater or even surface lakes that pooled within impact basins. Like the southern highlands, the battered and altered landscape of Arabia Terra is another testament to Mars's violent youth, a story of impacts, volcanoes, and water, all driven by the engine of its lumpy, chaotic interior. Perhaps the most profound consequence of Mars' chaotic early history was the loss of its global magnetic field. The crust of Mars contains remnant magnetism, proving that it once had a powerful magnetic dynamo, similar to Earth's. This magnetic shield would have been critical for protecting the planet's early, thicker atmosphere from being stripped away by the solar wind. A stable atmosphere is, in turn, critical for maintaining liquid water on the surface. So what killed Mars' protective shield? The dynamo was powered by convection in the planet's molten iron core, a process that requires heat to be efficiently removed from the core into the overlying mantle. The shutdown of this dynamo, around 4.1 to 3.8 billion years ago, is a hot topic of research, and the clues point back to the mantle. One leading hypothesis is that as the mantle cooled and released its water and other volatile elements through volcanism, it became stiffer and less efficient at convecting and carrying heat away from the core. This drying out of the mantle would have slowed core cooling to a crawl, eventually causing the dynamo to sputter and die. But another fascinating possibility is that the giant impacts of the late heavy bombardment played a direct role. A single, massive impact, like the one that formed the Hellas Basin, could have deposited a tremendous amount of heat into the mantle. This would have disrupted its convection patterns and dramatically reduced the heat flow out of the core. Scientists estimate that a reduction in heat flow at the core mantle boundary of as little as 10 to 40% could have been enough to shut the dynamo down for good. The timing fits perfectly. The Martian magnetic field died right around the time of the late heavy bombardment and the formation of its largest impact basins. In the end, The planetary scars of Mars, its global dichotomy, its colossal impact basins, and its ancient volcanic plains are all surface expressions of a chaotic and turbulent interior. The lumpy, heterogeneous mantle revealed by InSight is the physical record of the planet's violent formation and the intense bombardment it endured. The lack of plate tectonics, which on Earth erases the past, has turned Mars into a unique laboratory for understanding how terrestrial planets form and evolve. By studying the scars of Mars, we are not just learning about a single planet. We are looking through a window into our solar system's violent past. Mars is a silent witness to a time when cosmic collisions were the norm, and the fate of young worlds hung in the balance. Its chaotic mantle, a relic of that long-lost era, is a powerful reminder that the path to a stable, habitable world like our own is far from guaranteed, and that a planet's most important secrets are written not just on its surface, but deep within its heart. Thanks for joining us on Fun Facts Online.